we focused for a bit now on the moment of inertia. So moment of inertia is the analog of mass in rotational motion. Now we want to focus on the analog of force in rotational motion, so something called torque. The torque is equal to the moment of inertia times the angular acceleration. So exactly how in regular force, the force is equal to the mass times the acceleration. The torque is found by taking the cross product of two vectors. So the lever arm, or the radius vector, which points from the axis of rotation to the point where the force is being applied, and you take the cross product of that by the force that is applied to the rotating object. The cross product is a way of multiplying two vectors, and it is different from the dot product or the scalar product that we did before. So in a cross product, you are taking two vectors, you are multiplying them by each other, and you're doing that to find a new vector. So here, what we're trying to do is we're trying to find the product of the perpendicular components of the two vectors. So that means that if the two vectors are parallel to each other, so they're exactly in line with each other, then the magnitude of the cross product is 0. And if the angle between the two vectors is 90 degrees, then the cross product is a maximum, with it being the product of the lengths of the two vectors. So for two vectors with an angle between them, so let's call it theta, then the magnitude of the vector is the product of the two magnitudes times the sine of the angle theta between the two vectors. Notice if theta is 0, then sine of 0 is 0, and if the angle is 90 degrees, then the sine of 90 is 1, so it again becomes the product of the two vectors. So what we'd like to do is we'd like to find the torque, which is this cross product between the lever arm r, which is the vector from the axis of rotation to the point where the force is applied, and the force that's applied. So that means that the torque is proportional to the force applied. The larger the force, the larger the angular acceleration. The torque is proportional to the lever arm. So the further away you are from the rotation, the larger the torque. So think about trying to open or close a door here. If you grab the handle on the opposite side of the hinge, then the door is pretty easy to move. If you try and close it by pushing it right next to the hinges, it's much harder, and you might have a little trouble trying to close the door that way. So the point here is that with a larger lever arm, you have a larger torque, and with a smaller lever arm, you have a smaller torque. Lastly, the angle between the forces matter. So if you take a wheel and you push directly along the radius, the wheel's not going to turn, right? You're just pushing straight into the spokes. The angle between the force you are applying and the lever arm is 180 degrees in that situation, and the sine of 180 is 0. On the other hand, if you grab the wheel and you push or pull parallel to the wheel, then it's going to turn pretty easily. I guess you can say if you're driving a car and you have your hands at 10 and 2, then if you push your hands in trying to crush the wheel's not going to turn. But if you push or pull parallel to the steering wheel, then the wheel's going to turn perfectly easily. I guess the figure here, this kind of shows this as well. Let's say our pivot is like a seesaw. So that means that if you push, the seesaw isn't going to move, sort of push straight in towards the pivot point. If you pull, the seesaw is not going to move. But if you push up, the board's going to move up pretty easily. And if you push down, the board's going to swing down, no problem. So the key is to have a torque that the force needs to be perpendicular to this moment arm. Okay, so hopefully we understand the magnitude of the torque, but what about direction? We're trying to find the perpendicular force product between two vectors, and we want the final product to also be a vector. The torque is a vector just like force is, so we need to find the direction of that vector. To do this, we need to use the right-hand rule. So earlier we used one version of the right-hand rule to find the direction of the angular velocity and the angular acceleration vector. To use the cross product right-hand rule, the way I do it is I take my index finger and I point it along the lever arm vector, so that's the R. Then I point my middle finger in the direction of the force. So that means then your thumb is going to be pointing perpendicular to the pointing finger and the middle finger, so the thumb is pointing in the direction of the torque. So in the case shown here, the lever arm is pointing to the left, the force is pointing out of the page, and that means the thumb is pointing straight up as it's shown, so that's telling us that the torque here is pointing up. Okay, so the right-hand rule is one of these cases where teaching online really causes some issues. There's a few different ways people can explain it, so I do it the way I like to do it, but there are other ways of doing it that works. So what I'm going to do here is I'm going to give you a few problems to work through. So one's going to be about a crane to help you visualize kind of the forces involved. Basically, you've got a crane here, and then a weight force is pulling it down. And then we have a more general version of the question where the forces point all different ways, so you can practice. So what I'm going to do this time is I'm going to give you a practice version in the classwork directory, and then that's going to be followed by a version for points. So the idea is you can just practice your right-hand rule here as many times as you want. So you can click on this new problem variation, try all the different variations. It's not for any credit or anything, it's just for practice. But then after that, then there's a second version that is for points. So it should be pretty clear. The one that says new problem variation, that's the one that is for practice. And then the second one is the one that's actually for credit. All right, good luck.